Okay, so this video is going to be about enthalpy and stoichiometry. So remember that enthalpy is H, and that the units for enthalpy is kilojoules per mole. And because it has kilojoules per mole, we can use enthalpy to convert between units of kilojoules and units of moles. So think of it like another conversion factor, like our molar mass or our molarity. So we can look at enthalpy as just H, or remember, if it's the change in enthalpy, it's delta H. And we are going to do some stoichiometry problems with that information. So example number 1, if you have 2.5 grams of methane and it's burning, so now we're talking not just delta H in general, we're talking delta H of combustion, so our molar heat of combustion. It releases 125 kilojoules of heat, and you are looking for the molar heat of combustion. Now, again, we need to be careful with what we're talking about. Molar heat of combustion is our delta H combustion, but heat is just kilojoules, while molar heat of combustion is kilojoules per mole. So I want you to be very careful when you're reading these problems. Heat and enthalpy are different because heat, we're just talking about how much energy is being produced or absorbed, but with enthalpy, we're specifically talking about how much energy is produced or absorbed per mole. So that means two different things, and do not mix those two up. So if you see kilojoules by itself and you don't see a delta H or an H by it, then make sure that you know that that is heat, not enthalpy at this point. Okay, well, if we want to get our molar heat of combustion, we need kilojoules per mole. Well, we are given kilojoules, so we have 125 kilojoules, but we will need to divide it by our moles of whatever we're combusting. In this case, it's methane, which is CH4. And that will give us our delta H, our molar heat of combustion. But we do not have moles yet, but luckily we do have grams. And in order to go from grams to moles, all we have to do is use our molar mass. So if we have 2.50 grams of methane, we can convert that to moles of methane with our molar mass of methane, which of course you get from the periodic table. You guys have been doing this for a while, so that should make sense. We are taking old concepts and mixing them in with our new concepts. Alright. So once we convert to moles, our answer is 0.156 moles of methane. That's because we have 1, 2, 3 sig figs. So remember, this is what we're going to use to get our molar heat of combustion, because molar heat of combustion is kilojoules per mole. We know how much heat was released, but we want to know how much heat is released per 1 mole of methane. Well, this is not 1 mole, this is 0.156 moles. So again, if we do our division, it will convert it to our molar heat of combustion. So kilojoules divided by our moles will give us our molar heat of combustion. We want 3 sig figs again, so 801 kilojoules per mole. And that is molar heat of combustion because it is now kilojoules per mole. Kilojoules by itself is just talking about heat. Moles by itself, just moles. All right, so let's do another problem. Remember, our delta H is going to be our conversion factor when we are doing these stoichiometry problems. All right, so here's another problem. We have this reaction here, and we are given a delta H. Every time you see a delta H, I want you to rewrite it. I want you to rewrite it because if it's delta H, it is implied that it's per mole, and I want you to be able to visually see that. So rewrite your delta H as 5.4 kilojoules per 1 mole. What are we working with? We're working with chromium oxide. Woo, ran out of room there. Let's scoot over a little. Oops, not that much. All right. So we have our delta H, which is 5.4 kilojoules if there is 1 mole of chromium oxide. Well, when the experiment was run, we saw that 6.18 kilojoules of energy was produced. Now remember, this is not our delta H. This is just how much energy was produced because it's just kilojoules. And we want to know our mass. Well, remember, delta H is going to convert between kilojoules and moles. And once we have moles, we know we can always use our molar mass to convert to grams. So we're going to start with our kilojoules produced. By the way, it's close to this 5.4, so it's going to be about 1 mole, a little more. Now, see how this negative number is here? That negative number is important because it tells us the heat flow for our enthalpy. So where was the heat going? Was it going out of the system or into the system? So remember, negative is exo, so it's leaving the system, it's going to the surroundings, and positive is endo, it's going into the system from the surroundings. Now, because we're looking for mass, we do not need to include this negative number in our calculations because we don't get a negative mass. We're just told that this is where the heat is going. The heat is actually leaving the system when this reaction occurs. So the other thing is, where are we going to put our kilojoules? Well, remember dimensional analysis, if we have 1 unit on top in the next step, where does that unit go? On the bottom. So we're going to put our 5.4 kilojoules down here. We're going to put our 1 mole up top. And then our very last step, because we do want grams, not moles, is, guess what? Our molar mass. So we need our molar mass of our chromium oxide, which is 99.993 grams per 1 mole. And if you look at your dimensional analysis, kilojoules cancels out, moles cancels out, we're left with grams. That's what we wanted because mass is grams. So we've done our dimensional analysis correctly. Plug it into your calculator. I want 12366, so your answer should be 114 grams. So again, this is another way that we can use delta H as a conversion. So let's do one more problem.
Good morning. This is a quick announcement. If you are visiting the school this morning, or if you are a teacher that parks in a reserved parking spot in the front of the school,
I think I missed it.
please hold your vehicle. The reserved
There we go.
spots are already filled.
We're just going to go back and forth. All right. Example 2. All right. Okay, so here's our next reaction. We're given a delta H again. So remember, I want you to take your delta H and rewrite it as kilojoules per mole of whatever we're talking about. We're talking about glucose. And again, because we are not using delta H as which way is the heat flowing, we just are using it as a conversion factor, we're not going to take this negative sign. But this negative sign tells us that the energy is leaving the system, so that means this is an exothermic reaction. Okay, so we're going to start with our 1 gram of glucose. We eventually want to figure out heat. Now remember, enthalpy is heat per 1 mole. We just want to know how much heat was produced in this reaction. Well, if we have 1 gram of glucose, we don't have 1 mole of glucose, so it's going to be a smaller number, but we can use our dimensional analysis to figure that out. So we're going to start with our grams this time, and since we're starting with grams, we need to convert to moles, and from moles, we can convert to kilojoules. Now, grams to moles, we use our molar mass. And now we know to go from moles to kilojoules, we use our delta H. So that's what we're going to be doing. If you follow the units, you can figure out the dimensional analysis. And this is just what we've been doing with a new conversion factor. Alright, so the molar mass of glucose is 180.156. And use the messy writing. And then our next step is when they're now in moles, but we want to go to kilojoules, so we have to use our delta H. And let me just write. So we're going to plug in our delta H. And this time the kilojoules are on top because we're solving for heat and we're trying to get rid of moles. So again, if you follow the units, you know which way you're going. Alright, so let's take a look at this. So grams cancels out, moles cancels out, we're left with kilojoules, so we're good with our dimensional analysis, we just have to solve. And so the answer, again, 266 for this one, is going to be 16 kilojoules. Alright, so make sure that you practice doing these enthalpy problems, and also remember that when we are talking about enthalpy change, we need to know if it's positive or if it's negative. So positive means that we're adding energy to the system, and negative means that the system is losing energy. So this one is endo, and this one is exo. And as for the graph, remember if the reactants are down here and the products are up here, and this is energy, if the products have more energy, that means that you had to have added energy into the system. So that's endothermic, right? If the products have more potential energy, that means that energy had to have been added, because we don't just create energy, so it must have been added from the surroundings to the system. If it's the opposite, if our reactants had more potential energy, but by the end the products had less energy, well, that means that the energy had to go somewhere else. So it had to leave the system, and that would be exothermic. All right, so make sure and study this.